Hi there, this is Math 7, Unit 2, Lesson 10. We are introducing graphs of proportional relationships today, and we're going to see how graphs of proportional relationships differ from graphs of other relationships. And you began today's lesson, again this is always just a little recap of the lesson, then we'll get into the homework. You began today's lesson with some points that I asked you to plot. Remember our points, this is the x value and this is the y value. And so our initial part was plotting 0, 10, which is plot right there. 1, 8, which was right there, 2, 6, which was here, 3, 4, which was there, and 4, 2, which was there. When you plot those points, what are some things you notice about them? You might notice, for example, a couple things. We might say that these points all seem to line up, don't they? They seem to line up and make a line for us. That's one thing we notice. If you connected them, you could actually make a line. And you might also notice that the pattern here seems to be the same once again. It's going down 2 and over 1, down 2 and over 1. So there's lots of things you might have noticed with your classmates happening with this graph with just points there. There definitely is something taking place. We know it's going down as well. That makes it interesting, right? So it's usually a lot of our graphs so far have been kind of going up and things like that. This is going down, which is just different to look at. All right, we know our origin is over here. This is our starting point for lots of graphs if we're starting at 0, 0, but we're starting up here at 0, 10. So just some things you might notice as you take a look at that graph. When you look at a chart, for example, or a table, we've talked before about tables and that you might have a table to show some information. In this case, it says some t-shirts cost $8 each. So we know that the price for one t-shirt is $8 each. And that's represented over here in this graph. We have x and we have y, and in terms of what x represents, x is going to represent the number of t-shirts, okay, and y is going to represent the cost, because if I have one t-shirt, it's going to cost me $8, okay. In terms of our k value, our constant proportionality, our y over x, our y is 8 and our x is 1, so our constant proportionality is 8. Okay, so we know our t-shirt is the x value, our cost is the y value, and the proportional relationship, we look at it, should be 8. I can verify that by taking that constant proportionality and putting it in place here and just double checking. 1 times 8 is indeed 8, 2 times 8 is still 8, 3 times 8 is, 2 times 8 is 16, and 3 times 8 is 24, and I can keep on moving down and find some other ones and make sure that indeed there is a constant proportionality that makes this a proportional relationship. Okay, now these are the t-shirt set, that's the table. You can take that table information and we can actually plot it down here on this graph. What we could say, for example, is that we know that one t-shirt, and notice this is going up by 2, so 2, 4, 6, 8, and 10. One t-shirt is going to cost $8 there. 2 t-shirts is going to be $12, $14, $16 there. 3 t-shirts is 24, so it's going to be about there. And 4 t-shirts is at 32. And 5 t-shirts is at 40. And 6 is at 48. So that's what a plot would look like in terms of the t-shirts down here in the bottom to label the graph, and over here the cost, okay, for how much it would cost. These points, while they are in a line, right? Now we don't have to connect the line though. Keep this in mind. You don't always have to connect the line. We call these discrete points. We call them discrete points because the line is not connected. Okay, what we're seeing is that, well, if I'm buying t-shirts, I'm buying them in whole quantities, right? 1 shirt, 2 shirt, 3 shirt. I'm probably not going to buy 2.5 shirts, am I? That just wouldn't make a lot of sense. Are you going to go out and purchase 2.5 shirts? Probably not. Now, if you could buy 2.5 shirts, I suppose it would cost something along that much right there, right, to keep in that line, but you would never buy 2.5 shirts. So you don't need to connect those lines because these are discrete points. I'm only buying them in quantities of whole numbers, like so. There are other things that you can buy a part of something, right? So we'll take a look at that in just a little bit. Okay, so that was the basic part of what your lesson was today, was taking a look at what you did before tables, looking at the constant of proportionality to see if there's a proportional relationship, and plotting that down on some sort of plane. Okay, You then, with your table, with your classmates, were given some tables and some graphs, and I don't have that here to go over with you, okay? This was a class activity, and you had some tables and graphs, and what you're looking at is you're looking at what was the same, what was different about the various graphs that you had. And so you're just analyzing what kind of graphs you had and what was taking place within those graphs and having discussions about them. Okay? So in terms of the lesson summary for the day, we could say that one way to represent a proportional relationship is with a graph. Okay, and so here's a graph, for example, that represents different amounts that fit the situation of blueberries cost $6 per pound. So that's our situation we're talking about. Blueberries cost $6 per pound. So we know, for example, that if I have 1 pound of blueberries, it's going to cost me $6, right? So I have two different elements here. I have my weight in pounds here, okay, and I also have my cost in dollars here. So I have two elements that I'm comparing, the weight and the cost. So 1 pound of blueberries costs $6, 2 pounds cost $2. Now, if you recall before, with the last graph we saw, we talked about something being discrete being just the points. In this case here, I can have a line because I can actually buy 1.5 pounds of blueberries, right? I can actually buy that much, and if I bought 1.5 pounds of blueberries, that would actually be a point on the graph because I can actually purchase that. Okay, so in this case here, I can see different things. I can see that 2 blueberries, 2 pounds would be $12, 3, 18, and then even over here 27 would be 4.5, or 4.5 is 27. There's a proportional relationship there. You could turn that into a table if you wanted to, right? We could do our weight, and we could do our cost, and we can line it up like this, and we could say 1 pound is $6 and 2 pounds is $12, right? And so on, just like you've done before. And if we wanted to see, was there a constant proportionality? Sure, there would be. We have our x and we have our y, and we could say it's 6 over 1, which is 6, and verify that all these times 6 do equal the one beside it. So that's what that part looks like there. Okay, so this says, for example, we could, for example, buy 4.5 pounds of blueberries or 1.875 pounds of blueberries. So all those points in between actually could exist. Okay, so that's kind of the cool part about today's lesson. Okay, and we also talked about discrete ones, because you're making something like a sandwich, or before where you only have one, maybe you only have a price for 1 or 2. Anyways, our point here is that graphs that represent proportional relationships have a few things in common. So if it's going to be proportional, it has to have a couple things in common. It needs to be a straight line, and it has to go through the origin. These are key things here. If it doesn't have a straight line and it's not going through the origin, it's not a proportional relationship. That is very, very essential to what we're going to need to know going forward. It has to make a straight line, and it has to go through the origin every single time. So when you take a look at these guys here, these points, if I was to plot them out, go like this to this to this to this to this. Is that a straight line? Nope. Okay, they're not on a line, so we'd say not proportional here. Over here, is that a straight line? Yes, but what are we looking at? Does it go through the origin? Nope. So it doesn't go through the origin. It has to start at the origin here, and it has to be a straight line. It could be a straight line like that. It could be, if it starts at the origin, I can make it steep and go like that, but it needs to be a straight line, and it has to start at the origin in order for it to be a proportional relationship. Okay, so you're going to take a pause there and work on your homework, and then come back and let's check it. Okay, so here we are on tonight's homework. Which of these graphs could represent a proportional relationship? Explain how you decide. This is the key thing, to explain how you decide. You need to be able to explain it in words. So you have to be able to write something down and explain it there. Okay? So in terms of proportional relationship, we said it has to be in a line, and it has to include the origin. Those are the two things that it must be. And so when we look here, this is a line, yes, it includes the origin, so we could definitely say that A is going to be proportional. For B, it includes the origin, but that is not a line, so we would not go with B. So B is a no. For C, we include the origin, and it's still in a straight line, so we can include C. D is in a straight line, but it does not include the origin, so it would not work either. Okay, so those are the two common mistakes there. These are the same. Origin, origin, line, line, they're good. Okay, the next question says that a lemonade recipe calls for a 1/4 cup of lemon juice for every cup of water, right? So if I have water, which we'll look at the next page, and I have lemon juice, 1 cup of water to a 1/4 cup of lemon juice. Okay, so I already know right now that that is going to be, in a sense, my unit rate. This is going to be my constant proportionality, because 1/4 divided by 1, or y over x, is going to be equal to 1/4. Okay, let's see what we have in this chart here. Look at a table and use a table to answer the questions. What does x represent? X is going to represent the water, right? The amount of water that's going to be in this recipe. Okay, that's my H2O value right there. Lemon, the Y is going to represent the lemon juice. Okay, so my water and lemon juice, 1 to 1/4. We've already said before that if I look at the y over x value, the y over x is 1/4 over 1, which is simply 1/4. So my proportion, or my constant proportion, my k value is 1/4. In order to answer if there's a proportional relationship between x and y, I can put the 1/4 right here times 1/4 all the way down and see if I get the answer next door, so to speak. Okay, so let's look at 2. What is 2 times our constant proportionality? 2 times 1/4 is 2 over 4, which is reducing to a half. Does that match that? Yep, we're in good shape. Let's try this one over here. 4 times 1/4. 4 times 1/4 is 4 over 4, which is the same as 1. Does that match that? It sure does. Okay, and so I could check another one real quick. 6 times 1/4 is 6 over 4, which can then be reduced down to 1 1/2. Does that match? Sure does. And so we can see that we have a constant of proportionality. We have a proportional relationship between x and y. We would definitely say yes, that there is. Point B, question B says to plot the pairs in the table in a coordinate plane. So if you had some graph paper, it'd be easier to do than my little sketch here. But here's what I have. I have my water down below. I have my lemon juice here on the side. That's my x and my y. Okay, that's my x and my y. And for my water, I see I'm counting by whole numbers, so I can count it by 1, 2, 3, 4, 5, 6. And for my lemon juice, if I kept the same kind of space there, I guess I could do that. I have 1 is right here, and I have 2, and I have 3. But if I look at my things I'm using quarters and fourths. So if I take my 1, I can cut it in half about there. That's about a half. Here's about a half. And I'm doing quarters as well, so there's a 1/4 and 3/4, 1 1/4, 1 3/4 there. And so at 1, we are at 1/4, which is here. At 2, we're at a half, which is about here. I should plot back at 0, we technically are here, right? At 3, 1, 2, 3, we're at 3/4. At 4, we're at 1. 5, we're at a little bit more. And 6, a little bit more. Okay, so I end up with a line like so, starting at the origin, and off we go. I added that origin one in there because when I have no water, I also have no lemon juice. I do have a place where I haven't even started making the recipe yet, so I could pop that at 0. So it's one you might want to add in there to make sure you demonstrate that it is a proportional relationship. So that while that was on your graph, it's implied by what we know there. Okay. Number 3, decide whether each table could represent a proportional relationship. If the relationship could be proportional, what would the constant of proportionality be? We're trying to decide yes or no. So here's our x, here's our y. And what we can do is we can look at each value across the table and decide if it's going to be proportional. So this one is 3 over 2. That's our y over x. That's our k value. Should be the same. So 3 over 2. Here we have 6 over 4. 6 over 4 can be reduced to, well, 2 goes into there 3 times, and 2 goes into there 2 times. So those are matching so far. Looking great. 7 over 5. I can't reduce that anymore, can I? It's just 7 over 5. And we have one that's not matching. Well, let's check the next one. 10 over 8. 2 goes in here 5 times, and 2 goes in here 4 times. Well, that's not matching those ones there. To be a proportional relationship, this number needs to be the same for all values. So in this case here, we would say this is not proportional. Again, if you were to graph this out, right, and I had 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, what we're saying is that while this one might be there, and 4 might be at 6, 5 is just a little bit like here, at 7, and 8 was at 10 here. So this graph has, if I was trying to make you guess some points, it's like it's going like this, and then curves off. Something weird is happening. Either way, it's not a line. It's not going to work. Let's look at the next one. The distance you can see from a lighthouse. All right. Or from which lighthouse is visible. So here's our lighthouse, and the distance that can be seen. This becomes our x value. This becomes our y value. And to find our k, our constant proportionality, we're going to do y over x. So let's take a look at what we have. Here we have first 6 over 20. And 6 over 20 can be reduced. 2 goes in there 3 times. 2 goes in here 10 times. So I'm pretty good so far. Next one, I have 9 over 45. Okay, 9 and 45. I know that 3 goes into there 3 times, and 3 happens to go in here 15 times. Well, I already have 3 tenths and 3 15ths. Do those match each other? Nope, they do not. And since they do not, we would say these are already not proportional. I could continue, but really at this point, there's no reason to. I've already proven that 2 points on this line are already not on the same line, so there's no reason to go forward. And finally, number 4, select all the pieces of information that would tell you x and y have a proportional relationship. Let y represent the distance between a rock and a turtle's current position in meters, and x represent the number of minutes the turtles are moving. Okay, so we're looking at something like this. We're saying this is the minutes the turtle's been going, and this is the distance here. That's our y value. Here's our x value. Okay. And so if y equals 3x, does that represent a proportional relationship? So for example, if I had y equals 3x and I had some values, x, y, okay, and I plotted like maybe 0, 1, and 2. If x is equal to 0, what's y equal to? 0. If x is equal to 1, 3 times 1 is 3. X is equal to 2. 3 times 2 is 6. Okay. Am I getting a little pattern here? If x is equal to 3, 3 times 3 is 9. Okay, so if I did that, I would have a point that starts here at 0, 0, and 1, 2, 3. I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9 up there. And we can see that in this case, we are making a nice line, aren't we? Okay. So because I can plot that out, we're just starting with just some mystery numbers here, 0, 1, 2, 3, 2, 3, I can see and prove that this is actually a proportional relationship. It would work. Now, what we remember before, if it's in the form of y equals kx, that's in the right form to show that it is proportional. So that's definitely going to work. For B, after 4 minutes, the turtle has walked 12 feet away from the rock. So it's saying after 4 minutes, the turtles walked 12 feet away from the rock. It's just going to be like here, one random point. If I have one random point at 4, 12, Does that 1 point tell me there's a proportional relationship? Nope. It doesn't tell me anything. I could say that 12 over 4, y over x, 4 goes in there 3 times, and that's 1 time. I could say that, okay, well, that value is 3, that k is 3. That would be something that could work with this other information, but does this tell me that he's walking at a proportional rate? Does it say he walks at a constant rate? It doesn't say that anywhere. It just says that after 4 minutes, he's walked 12 feet. Maybe the turtle ran as fast as he could and then slowed down. I don't know if there's a constant value there. So while it might be a point that works with our graph, we don't know the information there to say that's constant. The turtle walks a bit, then stops for a minute before walking again. That's not a constant rate, and there are no numbers, so we can't use that one there. This one says, the turtle walks away from the rock at a constant rate. That's information that I need to know. I need to know that it's proportional. If it's a constant rate that it's walking away from it, then that would be something to tell me that it's proportional. If I knew this to be true, and that was always true, I could use letter B. I could. But if I don't know that, I can't use B. Hope that helps for your homework. Good luck on the rest.